To the club. So an ordinary sine function. I'll draw the sketch, but let me just put it into Desmos because why not, right? So y equals. If you go into function and tap on trig, you see all the different trig function. Well, trig functions that the calculator has stored. It's way more than what the TI offers, which is one of the reasons why I have to show you the TI stuff. Because if you go into a calc class being like, oh yeah, I'm ready to go for trig, I'm good to go with that because I got my Desmos, and the teacher's like, what the heck are you talking about Desmos? And all of a sudden you're like, oh, okay, TI doesn't do half the things that Desmos did. Now what? Right? So I got to show you both ways. But for now, let me just show you a nice looking sine graph on Desmos. Here's what a sine wave looks like. I'm just going to show you what we call period of the sine wave. And I'll just get the domains in here. I'll get into why these are what they are, or why they are the way they are in a minute. But for now, I'm just putting it in. All right, and let me just truncate it. All right, so this is an ordinary run-of-the-mill garden variety sine wave. All right. Goes from -1 to 1. And that's a good looking graph right there. Get rid of the grid. I feel like the grid just kind of takes away some of the oomph, some of the pizzazz, if you will. So let me get this in here and I'll just do a quick sketch. Markup, I mean. I already did the sketch. Look at that graph. Okay, so good looking sine wave. Now we'll do all the same stuff again, just with cosine. And again, you don't really have to create the graph on Desmos. So I'm just getting a little sketch here for you so you can see what it's all about. There's a nice looking cosine graph. There we go. Good looking graph there. All right. So the sine wave. Sine wave is, well, sine and cosine waves are both what we call periodic functions. And the good thing about periodic functions has to do with the name, periodic, in the sense that it occurs periodically. Yeah, okay. But also it's cyclical in the sense that once you establish what the overriding pattern is, that pattern will propagate out throughout its domain, right? Which means that this pattern is just going to repeat itself over and over and over again to infinity and beyond. And beyond. That's not a thing, I just always say. Right? So if you learn everything there is to know about one full cycle of the sine wave, then you know everything about the sine function. Same thing with cosine. But then you'll also see that there's a nice relationship between sine and cosine, to the point where if you understand everything there is to know about a sine function, and you also understand the relationship between a sine function and a cosine function, then you actually will be able to learn everything there is to know about all the other trig functions. That's how important this one function is. It's kind of like, it's analogous to the importance of a quadratic or a parabola. Like, why do you study parabolas so much? Well, because if you understand everything there is to understand about parabolas, then you can use that to understand cubics and quartics and other types of polynomial functions. Same idea here. So a sine wave always starts off at the midline. Right? So there's a line slices horizontally right through the middle of the graph. In most cases, in an academic sense, the midline will be the x-axis, right? But it is possible that the midline is not. Maybe the sine wave is shifted up, in which case the midline here, like for example on the Desmo screen, that midline would be at, for example, in this case, 1. Right? It's wherever the middle horizontal of the graph would be. Right? Make a little slider there. Let me show you real quick. Yeah, so no matter where you go with it, that midline is going to follow. All right, so we determine the important points of a sine wave based off of its relationship, or each of the points relationship with the midline. All right, so for example, this point here is at a maximum. This point here is at a midline, minimum. All the remaining points are on the midline, right? Or at least all the, and I say points, I mean the important points. Because yeah, there's points all along the graph, here, everywhere I can think of. All these points, they all exist on the graph. I don't really care about any of those, because if I have an overall sense of the structure of the graph, then I can just eyeball the curve as long as I know what the shape is supposed to be. If I know what an ordinary sine function looks like, and I know how it trends, then I can figure out everything else. All right. So what I would need to know is what the distance would be between the beginning point and the end point. The distance between the beginning point and the end point is known as the period of the function. All right. And that kind of makes sense because it's called a periodic function. It happens over the same pattern over certain periods. Right? I mean, a very simplistic example, teaching a high school. You have a 9-period school day. Each period is 40 minutes long. You could look at that as a cycle. Each class period is a cycle of 40 minutes. And in fact, if the education leaders had their way, it actually would be that. Every class would be structured exactly the same way. You take attendance in the beginning. Maybe you have like a little warm-up problem for the students to work on. Then you torture them for about 20 minutes. Or, I mean, you teach them for about 20 minutes. And then you let them practice problems independently. And then you close up the class in some capacity. Maybe take questions at the end. Maybe you give them a little quiz or something like that. But if you repeat that pattern over and over again throughout the day, you've just created a periodic function, right? And each period would have a length of 40 minutes, right? This is a more generalized situation where each period has a length of 2 pi units, but it really could be anything, right? The most typical thing that people think of when they think about a sine wave would be either a sound wave or a water wave. And with those water waves, for example, you have the crest and the trough. You know, you have the high point and the low point. The wave hits you, that's the high point, and then the water recedes, that's the low point. Out in the water, out in the ocean, you see the wave crests. You know, you see the tops of the waves, but then you also see the dips. Right? If you were to do a cross section of the ocean, you know, assuming that it's moving in a predictable sort of pattern, you'd be able to pick up those wavelengths, which is kind of cool. Right? I actually did a project with my pre-calc students in the high school where we had little wave tanks and we dropped objects into them, and we videotaped the propagation of the water wave throughout the tank. It happens so quickly that you could really barely pick it up with the naked eye. But if you record it and you go frame by frame, you could actually see the wave moving. And we used dye in the water, so it actually made it more obvious. It's pretty cool, right? But the height of each one of these waves, that's known as the amplitude. Right? Now that height could also be a depth. Right? So that amplitude could get you to the highest point, but it could also get you to the lowest point. Now, the frequency, we'll get to frequency in a couple minutes, but just in a general sense, because you really can't talk necessarily about amplitude without talking about frequency also. The frequency would be the number of entire cycles of a periodic function that you would have exist over a predefined period, right? So if I had more than one sine wave over this 2 pi period, then I would call this a frequency too, right? So I'll just show you really quickly. And we'll do more examples like this, which is why I'm just going to show you really quickly. It would look something like this. One wave, and then another wave. 2 full waves over that same period. Of course, it autocorrected the sharp edges. But 1 full wave, 2 full waves, right? Over the same length, 2 full sine waves, right? And based off this diagram, you can see why I have Desmos do my pictures. Right? But I could actually show you here by the equation. Just pop in a 2 here. That would be a frequency 2. Right? You have 2 full sine waves over the same distance, 2 full sine waves. If I put a 10 there, 10 full sine waves. If you go the other way and have half of a sine wave, all right, half of a sine wave over the same distance. All right. Sometimes you could have like really weird looking things, like an eighth of a sine wave. And you look at that and you say, at first glance, I mean, if I handed you this without showing you the scale at the bottom, if I handed you this and said, what kind of function are you looking at? And I gave you multiple choices, I don't know that too many people are going to just look at that and say, well, clearly that's a sine wave. You know, you might look at that and say, maybe it's part of a parabola. Or if you look at it too haphazardly, you don't look at it carefully enough, at first glance, you might be like, oh, it's a line. Right? So depending on the frequency, you could actually make something that looks very linear. I mean, I have a frequency of 1/16 here, which means over a 2 pi length, I have 1/16 of a sine wave. That looks very much like a line. That certainly looks like a line. I mean, it might as well be a line, you know? So that's one of the most powerful things about trigonometry, is that we could actually use trig equations in place of ordinary functions like lines, parabolas, and things like that. Because I mean, if you just look at this, that first arch, that looks like it could be part of a parabola. And you could actually get this, you can create a sine wave that would model part of a parabola. Right? So that's starting to get at the importance of why we're doing what we're doing. Right? So let me just do a copy paste here. We talk about the cosine wave. Just put in the plus A here. Same idea with the midline. As the graph goes, the midline follows. We're still looking at the same relationships in terms of amplitude and period and all that business. except I guess I made this graph a little bigger, so bear with me here. There we go. So structurally, it has the same ingredients, but it doesn't look similar enough for you to say that what I was saying before is actually true. And that is that if you learn everything there is to learn about the sine wave, then you'll automatically sort of understand the cosine wave, right? Because you kind of look at it and say, well, yeah, it's got the same ingredients, but it doesn't look the same. So let me show you how they could actually bear out the same way. And in order to do that, I'm actually going to take this right back to scratch. And I'm going to put in the standard, well, general form of a sine wave and a cosine wave. All right. We tend to use capitals. So A times the sine of B x plus C plus D. And we're just gonna make sliders for all these things. You get a nice sine wave there. All right. So one general form is A sine bx plus C plus D. And another general form is really the same thing, just with cosine instead of sine. So it's like, all right, same equation, just get out of here, sine. Let's get a cosine in there. All right, so all I would do here is in my Desmos, and I'll get this saved up for you, as I often, always, mostly try to do. All right. So I got my sine graph, my cosine graph. I'm going to make one red just so it pops out a little bit more. All right. So we were only looking at one period, but a periodic function repeats over and over again to infinity. All right. But if I take these two graphs and manipulate the sliders, you see how each one controls something else or some other aspect of the graph. Right? It's really up to us to try to figure out what each part controls. Like, for example, in the case, and we'll just focus on the sine wave for now. All right? In the case of the sine wave, the A value seems to be stretching it. Right? Stretching it vertically. Right? So you could call it a vertical stretch. Right? The amplitude is the absolute value of whatever the A value is, because it can be negative. But what it's going to do is it's going to give us a distance from the midline. All right, so it's a vertical stretch, but it's also, why did I do that? But it's also the vertical distance from the midline to the maximum point or the minimum point. All right. So I can just pop in the midline. So I'll just put that here. A note. The midline will always be y equals whatever the d value is. It's also known as a vertical translation, but we'll get to that in a sec. So I'm just going to type it in, y equals d. All right, so that's my midline. And you can see here that depending on where I move my d value, that controls the location of the midline. So we'll actually skip frequency period phase shift for a second and go to vertical translation. That's a vertical shift. But it also gives the position of the midline, which is y equals whatever the d value is. All right, so the vertical translation is whatever the d value is, but the midline is always going to be y equals whatever that d value is. Right, and I can turn on my cosine graph real quick, and you'll see that that relationship is true for cosine also. All right, frequency. We've talked about frequency in period already, but more of a hand wavy sort of way. But a frequency is going to be the number of full cycles in a horizontal distance of 2 pi. All right, so number of full cycles in a horizontal distance of 2 pi, that value is given by b, whatever the b value is. All right, so if I'm only looking between 0 and 2 pi, so I'll just zoom in instead of truncating the graph, but I'll only focus on 0 to 2 pi. I'm going to move my graph up a little bit. Let's just put it right here. Let's say I have a 1. Right, and we're looking at, let's say we're looking at just a sine graph with an amplitude of 1. I'm just trying to keep it as simple as possible for now. I'm going to put this at 1. I'm going to try to put it at 1. Oh, stay at 1. Stay right there. Okay. I'm going to put this at 0. And this is the other thing's fine where it is. All right, so we're looking at a full sine wave between 0 and 2 pi. Right. So if I change my b value to a 2, now I have 2 full sine waves. If I change it to a 3, I have 3 full sine waves. 4, 5, and so on. So that makes sense. But then you start wondering, well, what about negatives? Right. So negative b value. All right. It just changed the orientation, but it still has 1 full sine wave, right? Here's my positive 1. It goes up, then down, then back up again. But here, it goes down, then up, then back down again. But it's still 1 full cycle. Then 2 full cycles, then 3 full cycles. 4, 5, and so on. Right? So it's really the absolute value of whatever the b is that gives the number of full cycles in the horizontal distance of 2 pi. The period is the distance needed for 1 full cycle. Right? Now that's the first weird one. I mean, all of this is weird, but in terms of like, it's not, like the A, the B, the D, you just pull that right from the equation and it tells you something immediately, right? Here we actually got to start looking at something a little bit more than just a single letter from the equation, right? So let me put this right back at 0, the D value that is. So this is just y equals the sine of x, all right? Now, to get 1 full cycle, I'd have to go out 2 pi units, 0 to 2 pi. Right. But if I make this a 2, now in order to get 1 full cycle, I don't have to go out all the way to 2 pi. That's 2 full cycles. I'd only have to go out to a single pi to get 1 full cycle. Here's 1 full cycle, up, down, then back up to the midline. So just this part of the pattern, that's half of that distance. Right, so it's not just a b value. It's got to be something else. Right. Now, if I change my b to a 3, Actually, let me make it a 4. Keep the numbers a little nicer. Okay. So now I only have to go out to here in order to get one full cycle. All right, here's one full cycle of the sine wave. All right, that's one full cycle. That's a quarter of the distance. All right. So if b is equal to 1, a period is equal to 2 pi. If b is equal to 2, the period is equal to pi. If b is equal to 4, for example, then pi over 2. The relationship here is we're taking the initial period of 2 pi and dividing it by the number of full cycles that exist over that interval. Because if I take the 2 pi and divide it by the 4, I get pi over 2. That's 2 pi divided by 4. If I take the 2 pi and divide it by 2, that gets me to the pi. So what we get out of this is a rule. If we take 2 pi and divide it by the frequency, that's going to give us the period or the distance needed for one full cycle for any trig function. All right. So you could actually kind of draw that up in Desmos and make that a rule. The problem is, I'll just show you why it's a problem. If I put in 2 pi and the b value, it gives me a decimal response. All right. And it'll change depending on what I make my b. So if I put my b here at 2, for example, you look at that and you see 3.141, blah, blah, blah. That's great. I mean, most people can look at that and say, okay, that's pi. But what happens when it's like 5? Stay on 5 for crying out loud. It's the static cling. I'm just going to type it in. All right. So if the b value is 5, I see this decimal. I can tell you there's no way I'm looking at that decimal and saying clearly that's 2 pi over 5. You know. So for this case, we need a rule because it's not gonna work out as nicely unless you do it like this, which is to say you take the 2 pi, you divide it by the b, and then later on, and you can't even do it in the same computation. You would have to later on multiply that by the pi. So I'd look at this and say, all right, I got 2/5 and then slap a pi on that to give us the period. It ends up being the kind of thing where it's more trouble than it's worth, so we don't even bother. But this ends up being a nice rule, 2 pi over b. It's not overly complicated, so most people don't go looking for a shortcut for it anyway. All right. So we have amplitude, we have frequency, we have vertical translation, we got the period. One thing left is the phase shifting. All right. So phase shift, if you look at the c value here, moving the c will shift your graph left and right. So it's a horizontal shift. All right. But that horizontal shift is not simply equivalent to whatever the c value is. All right. That's where we kind of run into trouble. All right. This one I'm just going to give to you because it's kind of too complicated to try to discover, especially since I don't have my c value set up for increments of pi, and it's not easily done using Desmos. Right? So I can tell you that the phase shift value is going to be equivalent to negative c divided by whatever the b value is. Right? So the horizontal shift in the graph is equivalent to negative c divided by whatever the b is. Right? So let me just show you a sine wave, an ordinary sine wave. All right, so typical sine wave, pretty standard. All right, and then let me show you the cosine wave. Okay. Now, I'm going to turn off the cosine wave, and I'm going to shift my sine wave. All right. I'm going to shift my sine wave by pi over 2 units. All right. So it's hard enough. You can't get it to land that way on a slider. So I'm going to shift it pi divided by 2. All right. That should look just like the cosine wave. Right. And in fact, that is the cosine. I could shift it to the left, or I could shift it to the right, but I'd have to shift it more than just pi over units. If I shift it one way as opposed to the other, I'll still get eventually to a cosine wave. It'll just take a little bit more of a movement. I'd have to move it -3 pi over 2. But that's a different conversation for a different day. But for now, what we get at is the idea that there is a manipulation that can be performed to a sine wave to make it into a cosine. All right. So, I could turn my cosine wave on now, but it's also shifted because it's based off the same C values. But if I put this, so if you kind of hold this in mind, right? So you just kind of burn that into your memory, put this back to 0, and look only at the cosine wave, you see that it's the same graph that we had up on the screen a minute. All right. So knowing how to shift one graph appropriately will help you get another graph. And there is a relationship between sine graphs, cosine graphs, and all the other trig function graphs like secants, cosecants, and cotangents, all that wonderful stuff. Right. So that's kind of a different conversation, like I said, for a different day. But in terms of actually constructing the graph, it's not really challenging, because if you really think about it, I'm giving you an equation and I'm giving you a domain. It's really just a matter of you mapping it out based off that information. So what I'm going to do is I'm going to actually modify this graph, this equation a little bit. I'm going to get rid of the cosine for now. And then I'm going to, if you remember the piecewise functions, maybe you try not to, but what I'm going to do is I'm going to put in a domain here that's going from A to B, right? Lowercase though. And get some sliders for that, all right? So sliders all over the place. A slider for the equation, and then a slider for the domain. And I'll even make a little note here that this is for a domain. All right. And again, I'm making these notes because this is going to go up on Blackboard and be available for you. So when it comes to making a graph, it's not going to be challenging, because even if you didn't use this Desmos calculator, you'd still be able to just pop it in, grab some coordinates, and call it a day. But what I would do is I'd look at my sine function and say, all right, what do I got here? Y equals the general form is A sine. General is the word of the day, by the way. Bx plus C plus D. So general is the word of the day. So I would adjust my sliders to account for the appropriate A, B, C, and D values. So in order for this to simplify down to that, the A value must have been a 1. The B value, which would be the number in front of the X, would have to be a 1. And then everything else would have to be zeros. Right? And in fact, if you replace this with a 1, this with a 1, this with a 0, and that with a 0, you'd get right back to this. All right. So that's what we would do here, which is what we had. Then I would input my domain A to B. Now here, it's trig function, so I might want to just type it in. So -2 pi to 2 pi. And the benefit of that is it'll only show up, the only part of the graph that'll show up is the part that I want. Now I'm going to put the grid back on, because as cool as it looks without the grid, it helps to actually have the grid so you can count boxes. But now it really is just a matter of counting boxes, because if I have a reasonable scale here, I'm going to be in pretty good shape. The problem is, and this is the only little twist on this process. You'll see in all these different graphs that pi has been given to be 4 units to the right of the y-axis. All right, so this is giving us an x scale. So the x scale is, or I could say equals, is means equals, right? I'll use actually a colon. Pi is 4 units. All right, which tells me that 1 unit, so divide by 4, pi over 4, so therefore pi over 4 is 1 unit. All right, so I'd go into my setup here, and I'd make my step, my x-axis step, pi over 4. And then zoom in so that I see those 4 boxes, and then work my way from left to right. All right. So -2 pi, negative pi. This really should be like a tick mark, not a dot. So I'll take that as a typo, because it's kind of misleading now that I think about it. People could easily look at that and think that that's supposed to be a point on the graph, and in this case it happens to be, but it won't always be. So, but anyway, we're going to have x-intercepts at -2 pi, negative pi, 0, pi, and 2 pi. We're going to have maximum points. And the good thing about, one of the many good things about Desmos is that you can just tap on those maximum points, it'll tell you where it is. But we know that it's halfway between -2 pi and negative pi. As long as I have a reasonable scale for my y-axis, they're going every 2 boxes is 1 unit, and that seems reasonable. So point, 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 and point, and then a nice smooth curve, best you can. Through those points. If you miss a point like I just did, just make point bigger. Cover up the imperfections. So make up for a trig graph. And there you go. All right. And you'll notice that at no point did we figure out a table of values or anything like that. It's just noticing the trend. And there's no expectation that these values along the way, like all these points, there's no expectation that they're going to be perfectly accurate. They should just be in the neighborhood. Right. But that's really it. As long as you could put the appropriate information in, you're in good shape. Right. So you put in your domain. You put in your equation using the appropriate sliders, the coefficients. You put in your domain, and then you just make sure that your graph setup is good. Your step should be pi over 4. I can tell you right now, it should be pi over 4 for every problem that we do. Next class, I'll take you through the TI approach, just because I'm looking at the clock right now and I didn't realize that we're way over. Well, we're over time by my clock. I mean, we're still early, but no. But yeah, that's really all there is to it. So there is some other stuff on the TI. Oh, I gave the word of the day a few minutes ago. I think I might have said it after you put this message in here, though. But anyway, it's been done. Anyway, so with that in mind, what I'll say is if you could try the next couple of problems for the next class, just try. That's where we're going to start next time. So we'll do numbers 2 and 3 together in the beginning of class. Then we'll go back and grab that unit circle review, and then move on to some of the crunchier problems. Then we just have to tackle a word problem or two. But like I said last time, the inverse trig functions, honestly, I'm not really sure how this ended up in this packet. If anything, it should be in unit 3 because it's an optional topic. It shouldn't even be here. So that shouldn't be, that's not part of this unit. Shouldn't be here. But then we got to do some trig function modeling, and that's going to be the unit. All right, so we are now officially at long last in the home stretch. All right, so let me stop the recording.